Okay, so this is our final step. Now that we have our differential equations to describe that electric field in its y and its x components, you would think that, I want to know these electric fields. I'm integrating across the length. I know what the length of the wire is. It is something I can measure. So I can just go ahead and plug in. But you're gonna have to be wary of certain things. For example, look at this wire. Isn't there some symmetry here we can immediately use to our advantage? Take a look at the charge at the end, dq, and at some infinitesimal length dl. Over here we said we got this electric field here. But at the same time, suppose we consider another charge, or let's say this charge all the way over here. This dq at that arbitrary infinitesimal length dl. It's basically the same as the first one we chose, just on the opposite end of the wire. So let's consider that electric field due to this. We see that we also get that differential electric field. It's in now if we break this down into its components, we see there is dEy and then there is dEx. Now if you look at this carefully, what you see is that the electric fields all in the x direction will cancel out. Meanwhile, the electric fields in the y direction will add together. So before we decide to go willy-nilly and solve these differential equations, we should always beware of symmetry. Sometimes we might not even have to solve all of our differential equations. Just by looking for the symmetry here in this picture or scenario, we don't have to worry about one or more of these differential equations. Luckily, this is a uniformly charged object, so even if we considered, let's say, two arbitrary lengths or an arbitrary point here, at let's say L/4, we know that the x component of a charge at, let's say, over here, L/4, will cancel out in their x components. So sometimes looking for this symmetry helps to greatly simplify the problem, because now we know we don't have to consider this differential equation. For if we do integrate across it, it will be zero anyway when we plug in our bounds. Okay, that's good news for us in this example. So all we have to do now is simplify our differential equation that we have in the y direction. So let's go ahead and do that. So going to just go ahead and rewrite that equation like so. I see that there's a lot of constants I could pull out of this. So like k, like a, and q for sure. Right? And then what's left inside the integral would be 1 over L times L/2 squared plus a squared to the 3/2. And this will be across dl. And I know what the bounds of integration are for the length of this wire. So that's just from 0 to L. A length can't be less than 0. It can only be greater than 0 up to the total length of that wire. So now this is our final differential equation, and this is what it will be. upon integration. So that's basically it. I'm not gonna do the math on this one. The point was to show what the modeling approach was. Okay, so now in another video we'll go into looking at some examples and we'll move along quicker, but we will still adhere to these steps.